Alrighty, good morning everybody, and thank you very, very much for joining us at reInvent. I hope the keynote was inspiring as well as educational on all the cool things that we are launching. I am Jinesh Warrior. I am one of the technology evangelists and mobile and IoT team, and I'm also the track owner for the mobile and connected devices track. So with that, I would like to welcome you to this new track as well. I've been at Amazon almost 8 years, and I've not been so thrilled until now when I get to talk one of my favorite topics, which is Internet of Things. So it's a great opportunity, as well as it's a great way to actually learn directly from our customers, as well as our partners who are building great platforms on top of AWS. How many people are currently, so to speak, working on Internet of Things space? Oh, wow, awesome. That's pretty cool. So the customers and the partners that we have today that are planning to speak today, they are experts at what they do and have been in this and learning and breathing and living this almost every single day. So they have lots of different great ways to talk about best practices, as well as different ways of what they can share about from different angles as well. Internet of Things means different things for different people, but from a personal standpoint, I feel it's a dramatic and a massive shift towards where the world of connected devices is going. There's massive amounts of data, connectivity, protocols, management, data management, visualization, all connected back to physical devices. And we had an awesome Internet of Things hack day yesterday, where people got Intel Edisons and Spark cores to hack things and build what we call a connected maraca, a toy that you shake up to actually send data to AWS cloud services. In this talk, we want to really focus on some of the best practices from the experts who have been doing this almost every single day. And I want to also emphasize that because Internet of Things is such a massive shift happening, this is all pretty new. We are evolving as we go, and we are learning as we go. So from connectivity to machine learning, everything is connected to the world of Internet of Things. So with that, I'd like to kind of tell kind of our agenda of the presentation is that there are going to be 3 speakers, each doing amazing things in the Internet of Things space on top of AWS clouds. They are building a platform as well as a services infrastructure that makes it extremely easy for customers and developers to take advantage of the new space in a different way. From user experience to scalability to protocol management and translation. Now, you will see all these different best practices from different angles on a real-world stories. This is what I think I really like when I talk about, when I'm evangelizing about AWS, is like it's not just what we talk about our services, it's how our customers actually use our services is the best way to actually show the power of the platform itself. So we have 3 customers today that are using AWS in a very innovative way for Internet of Things. Spark.io is a really cool startup, has done some amazing things, and they are going to, we have Zach from Spark. Telemetry is going to focus on protocol translation and how rules engine and everything works together. And we have Kyle from Telemetry, as well as we have John from Machine Shop, who's going to focus on the value of the services framework on top of AWS itself. So with that, I would like to invite Zach Supala, CEO of Spark.io, to just take the stage. Thank you.
Thank you. Thanks very much. Hi, everyone. My name is, can you hear me? Yeah? Cool. My name is Zach Supala. I am CEO of a company called Spark.io. We make development tools and a cloud platform for companies who are building connected products. Like that. And there's our logo. All right. All right, so this is what we do. So we have a platform we call Spark OS. And basically, when we started this company, the thing that we saw was it's very difficult. It can be very difficult to build a connected product. And a lot of the people who are interested in creating something that's connected to the internet, right? So as an example, connected light bulbs or connected coffee makers or connected toys are often companies that make coffee makers, light bulbs, toys, and don't necessarily have the expertise to be able to build the backend, right? I think there's a lot of sort of interesting stuff happening around this space, helping people make these products. And our model of this we call Spark OS, which is kind of a distributed operating system for connected products, where we provide software development tools and a software stack that extends from the devices themselves, which is going to be like firmware running on a small microcontroller embedded platform, up to the cloud, and into the interface, which is going to be your web app, your mobile app, your tablet app, whatever it might be. We also sell hardware development kits. This is the Spark Core. We launched this on Kickstarter last year in 2013. We've sold something like 30,000 of them so far to engineers, developers all over the world. We actually just launched its sequel, the Photon, this morning, 2 hours ago, which is a $19 hardware development kit using a Broadcom Wi-Fi chip. We've already sold 2,000 in the last 2 hours. So that's pretty fun. So we have this hardware development kit, and this is something that you can use to create a connected product. So here's some videos of a hackathon where we built a Nest-like thermostat in 24 hours as a team. And what you're looking at is in the upper left, we take the Spark Core, breadboard it with a bunch of the components like a temperature sensor and a display. We write some code, mill out an enclosure, and by the end of the day, we had this Nest-like thermostat that's sort of an internet-connected learning thermostat. This is open source and available online, by the way. This technology is also used in products that are going to market. So this is the Namiku, which is a connected sous vide, which is a sort of interesting kitchen appliance where you can cook food in a hot water bath for like 6 or 8 hours. It's like a really fancy crock pot. But it's internet connected so that you can track how the food is, like what's happening over the course of the day and make sure that it's doing what it's supposed to do and not burning down your kitchen. So I'm going to talk a little bit about our architecture and what we built. But the first thing I want to say is this is open source. So if you want to see this stuff in action and see how we actually built it, here are some of our GitHub links. In general, you can go to github.com/spark and see our whole stack. But in particular, the Spark server, which is our open source cloud connection, our firmware stack, and our protocol are all available online. So I'm going to talk about 3 things. I'm going to talk about scalability of a device cloud, security, and user experience. So first, to talk about scalability, this is a dramatically oversimplified view of most web services, right? Which is you have a bunch of users and you have a bunch of servers that are delivering content, and you're going to, basically you need a bunch of servers. It doesn't really matter which one any individual person connects to, right? Because they're sort of all delivering the same content hooked up to something behind the scenes to deliver that content. But devices are different. So if you ignore the cloud and you say, I have a light bulb and I have a phone and we're in the same room, we want to talk to each other, it's a one-to-one connection, right? I'm trying to connect to this device specifically that's in my home. And that's great, and it solves some of the problem. But then you run into the issue where you've got a connected light bulb, and you want to do things that look like coordinated behaviors, right? So you say, I want all the light bulbs out there to turn off turn on when the sun goes down, right? Which actually is a little bit easier to do by sending out signals from the cloud, because you can in one place track what time it is and what time zone all these different things in, and then just like send out messages as the sun sets around the world. So that requires coordination, which requires some kind of cloud service. And so suddenly your platform looks like this. So this is what might work in small scale, where you've got a bunch of these light bulbs hooked up to servers, and then you have users connecting to those servers and sending messages that get routed down to the light bulbs. Now you can see this isn't a design that scales very well, right? Because at some point, this really only works with one server, and as soon as you move beyond one server, you have what amounts to a routing problem, right? Which is basically people are going to come in and hit a bunch of different servers, and the light bulbs will be connected to these servers, and they may or may not be connected to the same server that the person's request gets routed to. And so what you end up with when you try and build out this backend is this general, like, I've got an infinite number of people with phones and tablets and web applications, and I have an theoretically infinite number of devices, and I need to make sure that the right message gets to the right place, and it happens quickly, and it's, and it's correct, right? And secure, and all the things that you want out of a web service. So this is what our infrastructure sort of looks like at a high level kind of way. What happens is we basically have two different services. We have an API service and a device service. And so the API service looks like any other REST API out there. It's, ours happens to be written in Node, but it could be written in a lot of different languages. And so we have them on different boxes, and we have elastic load balancing so that when these requests come in, it gets routed to one of these API services, right? And on the other side, you have the light bulbs or the devices, right? In our case, these development kits or products built on our platform that connect to another elastic load balancer and to a bunch of device services. Now, these device services are a little bit different than your typical web application because these are holding open long connections. So it's a TCP socket, and that way we can communicate with it in real time both directions. Otherwise, we'd have to have the device pull and check in every once in a while for a message, and that creates a lot of overhead that's unnecessary and also means that you're going to have some latency. You're not going to be able to communicate with it immediately. And so now we've got all these things hooking up to all these different API and device services, and somehow they have to communicate with each other. And so we have a bunch of message brokers. So we basically have devised a sort of message queuing system to make sure that each of the API services and the device services knows who the other are and can route the message correctly and be able to get the message back and forth to the device quickly. So that's sort of generally how we solve our scaling problem. Let's talk about security. Connected devices don't look like computers necessarily. I mean, they are computers, but they don't look like your laptop or your mobile phone. This is the chip that we use in the core. It's called an STM32F103. It costs less than $2, which includes memory and flash, which is good. It's cheap, in like 10,000 units. But it has 128 kilobytes of flash and 20 kilobytes of ROM. So you're not running Linux, you're not running Android, you're not running Windows. You're running bare metal code. Or at best, a real-time operating system. Oh. Yeah. So each of the devices, I mean, it's opening a long connection, but it's deciding which server to connect to.
We'll take the questions probably later on, so if you can hold off, that would be great. So let the presenters go back. But keep note of your questions. So
Yeah,
thank you.
Happy to answer later. Okay, very constrained environment, right? And yet the expectations for how this thing works are relatively similar to a web service, which is it still has to be secure, right? It still has to be fast, it still has to be reliable, even though you're working in this very constrained environment. And so what happens is you end up looking at the stack that you're used to using for a web service and basically ripping everything out and replacing it with something else that kind of does the same thing, but works in this constrained environment. So for instance, HTTP. HTTP is great, it's the language of the web, it's used everywhere, and yet it has these giant headers that don't seem giant to anybody who's working, on a PC, but for us, it's like, why do you need all that, right? What if that header were just 1 byte, right, or 2 bytes? And that's when you get CoAP. So CoAP is a new protocol that's basically very HTTP-like, but with these really short byte-efficient headers that make it work better in a constrained environment. OpenSSL compiles down to like a megabyte or something, so that's not going to work. PolarSSL is an open source version, except it's under a GPL license, so you can't use it in a commercial product, and the commercial license is super expensive. So turns out PolarSSL is there's a BSD licensed fork from an old version of PolarSSL called TropicSSL. So we use that. So we can have an open source security implementation. And instead of using SSL and TLS, which solve the problem for a web service, but have a lot of overhead that's often too much for a constrained device, we use RSA and AES encryption. So we're kind of like ripping out all the unnecessary bits of the SSL and TLS so that we can make it work in these constrained environments. Also, we end up doing weird things like provisioning keys on our manufacturing line. So this is the manufacturing rig that sits in the factory and programs cores as they go through, and it gives it, and this is where the keys come from, right? So it's like super weird and messy, and like we have to deal with what happens when employees in China pull out the power of this thing and like it resets the flash and all that kind of stuff. This runs on a Raspberry Pi, by the way. And then finally, to talk briefly about user experience. A lot of the user experience here tends to come from what happens when things fail. So for instance, when you try and connect a device up to your Wi-Fi network, this is the Wemo interface, and this is the LifeX interface for what happens when it doesn't work, right? So Wemo, looking for devices, it'll do this forever. That doesn't help you understand like what's actually happening, right? You don't know that it's not working. It's just like spins, right? Whereas LifeX has a much more useful right? And then links and things that you can do. You can try it again. You can change your settings. You can go to troubleshooting. It actually helps you when things fail. From a development perspective, we try and obscure, we try and make this stuff look a little bit more like the web, even though it's not. So like in order to take your teddy bear thing that can like has motors in it so that it can hug a kid, you post to the teddy bear's URL /hug, and it calls a function within the firmware, which makes it feel like you're accessing a normal web resource, even though it's this, teddy bear. And then finally, speed. Speed is really important because even though this connection is going out to the cloud and back, people expect this stuff to work real time, and that you just hit a button and something happens immediately. And so we focus a lot on making sure that our system is incredibly efficient and that we can get real-time communications through the system. So overall, scalability, it's a different kind of problem. Internet of Things connected devices work a little bit differently than web services. A lot of the same concepts apply, but have to be applied in different ways. Security is all about how do you get the same level of security in a constrained environment. And user interface experience, you have to fail gracefully. Thanks, everyone.
Thank you. Thanks, Leonard.
Yeah, for sure.
I totally agree with Zach here. Now, the traditional way of doing cloud architectures has sort of, we have to do some unlearning as well as relearning to really understand the power and then how technology can actually just disappear behind the scenes so devices can actually work just like the devices themselves while they are connected all the time. Next up is Telemetry from CEO of Telemetry, Kyle Roche. Thank you.
This thing on? Good? Can you hear me? All right. So my name is Kyle Roach. I'm from a company called Telemetry. I went backwards. So hang on one second. Yeah, all right. Spark is, I don't know. This device is not connected to us. Well, anyways, while we're fixing that, I can just use this thing. It's Windows, but we'll figure it out. There we go. So we fell for the logo slide already. All right, so to talk about kind of what we do and what we built on Amazon, I'm going to talk in context of one of our customers, one of the larger kind of traffic consumers that we have on our platform. We have a company called PeopleNet. They have 230,000 onboard computers from fleet machines online. Their kind of problem, to kind of walk through, what we met when we met them. These trucks have been out in the field for years, right? The first one they ever deployed was 9 years ago. There's a protocol invented by some guy in their IT department called Amir. He invented something called Amir's pretty simple protocol. This happens all the time, right? Somebody in IT has a great idea, they grow out of it eventually. So this thing's online for now 9 years. The first device they've ever deployed is actually still in the field, it's still live. So it's pretty kind of a stable, interesting use case. But they grow, right? They grow over time. They want to start monitoring the containers in the back, the freezer trucks, the high-value assets that they're shipping, something like that. Somebody else in IT has a brilliant solution for that. It's another siloed system. So now there's two different kind of protocols in play, two different backends, two different complete stacks for IoT. Over time, these guys get more and more successful. They grow by acquisition, right? So they start buying companies that come in with yet another protocol, another backend system. And this is the problem that they face. When they want to go into a new business model, I can't walk around without the clicker. I'm going to carry this thing with me. When they want to go into a new business model, like say, monitoring boats or monitoring something other than a fleet computer, they're presented with an interesting problem. What do they do about their old traffic, right? Do they continue down this path of kind of siloed systems? Or they go after like an SI approach where they want to go back, and then SIs are kind of like, this is awesome. We can go back and roll out new hardware, firmware updates, SDKs, and we'll forever be digging out of the same exact application stack you had already, right? So this is where we step in. So Telemetry is a platform that ingests something called SendML. It's a way to describe sensor-based protocols. You can post your SendML kind of description, your socket patterns, how your devices talk. Even if they're completely homegrown protocols, you can post that to our platform. We'll start listening and adapting to that type of traffic. Now, from there, you have choices. Once we kind of onboard everything, now, at this point, none of these trucks in the field have ever been touched by us. There's no new software push. All they did was move the TCP socket to our platform instead. Now we see everything in its native environment, so these trucks have no idea they've just been migrated. So now from here, we interop with other types of traffic, right? So now this next version of a device, they can choose to use something like MQTT or CoAP or whatever they want to build it on, and we'll normalize all that traffic back and forth for them. So that's kind of our position in IoT. It's a little bit closer to the industrial internet side of things rather than kind of the new, kind of cooler device stack. But from here, this is kind of an opportunity for them to start tracking everything in a uniform type of way. So without a huge capital expense, they can get everything online, start doing things that are more intelligent, maybe geofencing, routing, predictive behavior across all the different versions and protocols that they've been using in the past. And again, this is without touching any of the machines that are in the field. So some of the challenges that you see with these types of different data is, when you move from a siloed system, something that one single development team built from the ground up, they handled everything from user experience to security to data models and protocol patterns. You start to see a lot of odd behavior, right? Where especially this one, for example, over satellite connections, you get multi-part messages, different sensors that are reporting around the same logical device don't have any context about each other. So we handle things on the wire for stream processing that put these things back together. So the developer on the other end can see over a WebSocket and a JSON feed or an MQTT feed the reconstructed messages from all the disparate sensors that are part of that logical asset in the field. Now you also have the other problem, right? You have trucks that know too much. When they move from a siloed system, and this doesn't have to be a truck, it could be anything, but they move from a siloed system to the cloud, right? You get things like some of this data for oil and tires or whatever needs to go to maintenance, but driver hours, things like how many times they cross state lines, those are HR sensitive kind of personnel data, right? Now all of a sudden this truck knows things that it shouldn't know about personnel and things like that. So on the wire for these types of stream protocols, we'll take those, split them, and allow you to secure them differently for different groups as well. So that even though this legacy protocol was kind of built inefficiently, it comes out the other end over Amazon's, our platform on Amazon, kind of split and secured correctly. So you also have kind of interesting issues like, for example, geofences or machine lookups, right? So machines don't have context about what they're actually doing. So the truck, again, sometimes trucks are shared across multiple fleets. So we'll get reports about some sensor ID or an engine computer ID, but there's 3 different drivers that use that truck through the course of the week. So this forces the developer on the other end to do lookups in line, right? So it blocks transactions. So we built a system to allow you to do those asynchronously. We'll go back and reconstruct the sensor payloads so that when you do your reporting or your application pulls reporting, it has context around things like geofences or third-party system lookups, or you can even do kind of homegrown system lookups. Go back to your SQL server, pull something out, do some calculations, and stick it back in. When we see those reports return, we'll start sticking them back into the sensor messages that came over the wire originally. Now, this is all kind of basic threshold actions, right? You should expect this from any sort of decision system. IoT kind of forces a more interesting pattern, and Zach talked about that a little bit too, is where one device, that one-to-one relationship with a device isn't enough anymore. So what we had to do is kind of come up with a way to easily normalize, how do I make decisions across the aggregate of all my IoT systems? So we came up with kind of a familiar syntax. It looks like SQL. You can post what kind of look like SQL sentences or queries to our REST API. We'll start looking for conditions as they happen going forward. But this gives you kind of flexibility to look at not only like, is my engine temperature too high, but is it outside of 5% variance like on a Wednesday in Dallas when other trucks have the same sort of heat patterns, right? So you can post these really complex computational models we'll look for those in the future as they happen. Now from here we have an action engine. So this is kind of where our handoff to Amazon's core services happens. When these conditions happen, right, when we filter out something from a low-level protocol, you can start to do things on it. We can republish, we can transform the payloads, which you see in medical a lot, where we'll get binary data from a device, and then we'll spit out an HL7 record or some kind of template for another backend system like an Epic. And we also hand off to Amazon's core services. There's something beeping up here. Or it's voices in my head again. So we'll hand off to Redshift. A lot of our customers have Redshift as their, their kind of longer data warehousing analytics engine. So from here, our action support will hand that off based on conditions. And all this is really just to pull out, what's the signal? Out of all that noise, where's the one important piece that I needed to pass on to the actual decision system? So I won't spend a lot of time on this. This kind of leaks into sales and marketing. But on the right, I just wanted to talk about what we built on Amazon. From the right, coming in through any kind of IP network. So we'll support UDP also. For that, we have to go around the load balancers. Most of our traffic is load balanced. It's regionally aware through Route 53. So we'll route you to the most kind of least latent node, I guess. Through all these different inbound connections, we hit our Amazon cloud. And we go to market a couple different ways from here. So we have an offering on the marketplace. You can run our whole stack as an AMI if you want to run it in a private cloud. We also have a multi-tenant platform. Our multi-tenant platform is doing about 4 billion transactions a day right now. We have something over 1,100 companies using it. So they use it to map, like I said, legacy, enterprise, kind of low-level socket protocols to usable things like WebSockets and MQTT. So our stream engine kind of looks like this underneath, just a super simple what we built it with. The entire thing, the entire stack is written in Scala. We wrote everything ourselves. We do use Cassandra right now for our backend data store, but we're exploring Dynamo as kind of an alternative for that for many different reasons. Scala was a good choice for us because of the use of Akka and for distributed remote actor systems. And so what this allows us to do is basically take our architecture and split it among the most kind of intense the beeping is driving me crazy. The most intense parts of the inbound and outbound processing, right? So if certain protocols have a more intense kind of need on one end, we can scale those actors differently and spread those across nodes independently from actors that talk on the other end to things like Redshift or simple sort of transactions on that side. So all these things can be unevenly distributed. Now, just to kind of cover some of the practices that we see out there, and Zach touched on this too. So typical HTTP patterns, they work fine if you're building a new system. Most of the stuff that's already in here, already in IoT, or back when it was M2M or industrial internet, or if you've been around it kind of as long as we have, none of those things talk HTTP at all, right? They're talking low-level sockets. MQTT was something that we started with back in the oil pipeline. So that's been around for a good while. But this pattern changes, right? This one-to-one relationship between kind of an entity and the back end. And the reason is, devices need to talk to other devices. We've seen this a lot with control systems, right? Where take the oil pipeline again, where you have a bunch of different flow meters. They have to open and close valves down the line. That has to happen in real time. So the consumers and the producers, have to kind of have a relationship, but they can't put too much pressure on the actual consumer. So HTTP is kind of a hard pattern to work around for that. So we talk a lot about event-driven systems, pub/sub, and we're obviously big fans of MQTT. Our last company, we started with the guy who wrote the spec for MQTT, so it's kind of part of our background. But the pub/sub model looks pretty similar up front, right? Where I have a relationship with my broker. I can publish and subscribe on different topics, use different hierarchies to segregate my messages. But the key thing here is that the publisher and the consumer are fully decoupled. So the publisher has no idea who's actually listening down the line. So that gives us a whole lot of flexibility for command and control systems, but also to inject context into messages without putting any pressure onto the device. So the device that's originating the message only needs to send what he actually knows about, just sensor readings. So we can add context to it, inject things like geofences, third-party lookups, stuff like that, and the consumers are pulling that data in real time. So we talked about protocol overhead, which is interesting. When Zach mentioned that, we use this example of a postcard all the time. You want to write a postcard home. The postcard itself is the payload, right? So you get into kind of protocol wars about TCP versus UDP at the kind of core. But on top of that, there's a couple different ways to look at this. MQTT and simple things with small kind of fixed header size. It's like putting a stamp on the postcard, right? Just the bare minimum to get my payload delivered is kind of what I went with there. You look at HTTP, it's kind of an overkill. Google says HTTP's average header size is 700 to 800 bytes. That gets pretty expensive, especially over like a satellite or a distributed cellular system. That customer I referenced earlier, PeopleNet, if we save 1 byte per message in aggregate across their system, it's $11,000 in satellite savings per year. So things like this do add up over time, especially with legacy sort of industrial internet type use cases. CoApp's a great solution also, very small kind of overhead, 8-byte fixed header, and MQTT ascend, which is a variation basically over UDP. So you can get kind of that same pub-sub topic hierarchy pattern, but over UDP. Cool. I know we're jammed on time, so I'm going to kind of cruise through the rest of this a little bit. So one of the other things to consider is, in the field, especially in the field, protocol has an impact on battery life, right? You're turning your antenna on, off, you're keeping it on for keep alives, things like that. Now, it's interesting, if you look at HTTP versus MQTT, as much as we talk about MQTT, it actually costs less or costs more on the battery to start up. So that first message is a little bit painful, but over time, MQTT gets that back. So any connection that's going to last over 5 minutes, it's more efficient to take a socket-based keep alive protocol than it is to get that HTTP connection reestablished over and over again. So it spends a lot of time on, like I said, turning the antennas on and off, and then keeping that connection open so it'll wear down the battery. So yeah, if you can kind of see where that crossover is, it's right around 5 minutes. So quality of service, this is something very important to MQTT, and you can get these kind of QoS0 and QoS1 with HTTP-based pub subsystems also. But if you look at QoS1, that can survive a network failure. You can get it more than one time, and that might be okay for I want to report my run, to my iPhone or something like that. I don't ever run, but if I did run, I would not care if it came in more than once. But if it's a pacemaker, it's some kind of mission critical, system that can only get that command exactly one time. You have to use something called QoS2, right? It ensures that it can never be duplicated and also survives a network failure. So that requires a second round trip. So there's a little bit of an expense there, but these types of systems are harder to build over HTTP. They're more complex. One last thing on MQTT and these types of protocols. We have something called a last will and testament. So if I'm a device, I'm in the field, and again, not to put more pressure on me as the device, I want to be able to say to the backend, and to the platform that I'm talking to, hey, if you lose connection with me at any point, you got to handle telling all the other devices or telling the other backend systems kind of, this is what happened, and here's what I need you to do about it. So MQTT defines this last will and testament idea where this device 2, he can come online, he can say, hey, look, if I ever go away, you need to send this disconnected message to anybody else who's listening. Over time, that keep alive starts to go back and forth, it gets exceeded at some point, and the broker has to deliver this message on behalf of that device 2 so that everybody else in the system knows that he's gone. So you can't count on him to deliver it on his way down, or if he's going through a tunnel or something like that where the connection's lost. So last will and testament's important too for decision systems without putting the pressure on the device. So transient and durable sessions, this is one more advantage of kind of an MQTT-based system or a pub subsystem versus an HTTP. Sessions, when they're transient, they end, and any messages in between the sessions get lost. So on the left example here, message 3 is never delivered, right? So you can use durable subscriptions. The broker has to keep kind of track of what am I looking at, what did I miss when I was offline in between my sessions, so that over a really kind of unreliable satellite connection or cellular, I can go up and down all day long. Message 2 and 4 will be delivered as soon as I reconnect the next time. So we're going to hand this off to John. But yeah, some final thoughts. Basically, choose a protocol that fits. Look for things like message integrity from the platform you're using, and keep the devices as simple as possible. So thank you.
Awesome. Thanks a lot. Sorry for the beep. That's great. So as you can see, the concentration, like the elements that in the real world of IoT, where there are trucks and others, old protocols involved, you have to really understand the differences and the value that comes with co-op or MQTT and doing the protocol translation, how the request response sort of works, and how the new architecture evolves over time. So next up is Machine Shop, John Cox, and I would like to special thanks him for the last minute change. So thank you very, very much.
Thank you. Yep. gonna give this thing a shot. How's everybody doing? 3 of you are doing awesome. Good, cool. So I'm John Cox, Senior Director of Technology at Machine Shop. Let's see, no, it's not gonna work, there we go. So what we're gonna talk a little bit about is how we do real-time message processing and scalable API management with our platform at Machine Shop. I'm gonna talk a little bit about who we are, kind of what's under the hood, some customer experience use case type things, as well as a little bit of how we've evolved with AWS over the past couple years that I've been on board, and kind of the ease with which that has happened. So let's talk a little bit. So first of all, this is our Denver team at a very important team meeting. So I just wanted you guys to meet us. There's a few of us here. So let's talk a little bit about what we do. So where we stand at Machine Shop is kind of this intersection of APIs, and that would be APIs that we develop and expose around the Internet of Things, as well as aggregated APIs, third-party APIs that you would bring in from other services that provide context maybe to your IoT APIs. We have a business intelligence engine that allows you to create rules and alerts on various pieces of data that come into the system. And then finally, IoT is kind of the foundation that we sit on, and it's the background that we come from, and understanding how to connect physical devices, and not even necessarily physical devices, but data sources in general, with applications in a way that makes integration easy, seamless. Let's make the developers' lives easier. So this is in developer speak, because the last slide came from the marketing guy. This is kind of what we do, right? Heterogeneous data sources. Let's make that data easy to digest. Let's normalize it. Let's make it easy for applications to understand that, create universal contracts that make application development easy. Let's aggregate other APIs that provide context. Let's do it all in real time, and let's make it easy to talk to the Internet of Things, okay? Cool, so this is a picture of kind of how things work on us, right? So things starting, we're gonna start from the right side here and move our way through. Data comes into the system in real time. That could be things, Internet of Things type things out there checking in, GPS devices, security systems, temperature sensors, you name it, all kinds of protocols, Tower of Babel type of a situation. Everything reporting into us in real time, we ingest that, we run rules against that. Those rules are created through API calls. By the way, everything that we do is an API. We have UIs, GUIs, that go with those, but those GUIs are all just written on our APIs. So you're creating rules, you're polling for data, you're pulling that to create visualizations of your data, all that kind of good stuff. Business logic gets applied to that data as it comes through the system. It may generate alerts. It may set a trigger that says, wait for the next piece of information from this other thing over here. And if these two conditions are met or more or whatever the case may be, then do something with that. And then finally, over there on the left side of the cloud is our API management. So allow me to leverage what Machine Shop brings with user management and authentication and authorization and metering calls and all of those types of things, and apply them to third-party APIs that we want to aggregate and bring in such that we have sort of a one-stop shop for all of our application developers to build out applications on a multitude of different types of data that may be relevant for our particular business use case. So let's talk about a customer example. Let's ground what I just said in a specific example. And there's a lot of examples that I wanted to pull from. This one was kind of the most, I thought, interesting and unique. So just so that you know, there are other examples where we're talking about putting, dots on a map or creating dashboards or even just pure API management and being able to meter calls as they come through going out to other systems. This one is an interesting one because we're working with CSR. They're a chip manufacturer. They create a commodity. There's a lot of chip manufacturers out there. There's a reason why electronics are as inexpensive as they are. It's because of volume, right? And a lot of chip manufacturers, you can swap out one for the other. So as a business, how do you generate more value? How do you move yourself up the value chain? If I'm a chip manufacturer, I generate an SDK. That SDK is a little bit cumbersome to work with, and it usually requires a pretty specialized knowledge, and that SDK is for that one chip, and then you have 1,000 other chips that you create that all have their own SDKs. Configuration through those SDKs can be a little bit risky. So why don't we create a standard set of APIs so that any developer that wants to develop against that chip knows exactly how to do it and can do it through a RESTful API, something that they're very familiar with. So now I've opened up who can develop and command and control and configure and poll my chipset. I've opened up the market of people that can do that. And I've moved myself up the value chain quite a bit as a chip manufacturer because I've democratized that ability to develop against my chip. So that's what we're talking about here. The other idea here is, and I've said this a couple times, but how do I take third-party APIs and aggregate those in also to where it gives my chip, which is just a chip on a board, some sort of context that is specific to where that board sits and what it is doing at the time. And there are a lot of other value-added third-party APIs that you can pull in to do that. So just hopefully that kind of makes sense. Let's provide more value to our customers, because if we don't, we won't be there very long. So why do we choose AWS for what we do? I think this probably is not news to anybody. We don't want to tend to some sort of on-premise infrastructure. Why? We want to be able to have the flexibility to play with what we're doing. We're constantly iterating and evolving what we're doing and how we're doing it. And I'll show you a little bit about what that looks like. But we shouldn't have to think about CapEx, right? We should always just be thinking in terms of OpEx when it comes to this stuff, because that's way easier to get the thumbs up on and do something cool and new. And we want DevOps to be easy, because customer support needs to be easy. We need to keep our customers happy. So this is kind of what our infrastructure looks like, and why and how we evolved, right? So we can scale up super easy. We can deploy super easy. Anybody on the team can deploy super easily, and it's very, very low risk for us. We can change architecture whenever we want, whenever it feels like a good idea. In our staging environment, we can say, hey, this web server looks like it's gonna serve us a lot better on our public-facing APIs. Let's go try it out. We did that last week. It worked great. Clone, deploy, pull things out of load balancers, put them back in, and production is up and running with that new web server, in an afternoon. Sweet. The other thing that we've done is over the past few months, it took a few months, but it happened a few months ago that we cut over officially completely, is our original architecture was quick to get out the door, and it was sort of the bucket brigade of queues and workers, right? So something comes in, it gets queued up, a worker comes in, works on it, it passes it on to the next bucket, that gets worked on. So, a message comes in, it gets translated, it gets put in a bucket. Okay, then rules, are there any rules? There are. Okay, there are 5 rules to run on that gets queued up. Okay, are there any alerts that came out of those rules? That gets queued up, and so on and so forth down the line. We've moved that to parallel processing using SAMZA as a framework to do that, and the workers that go with that. Way fast, way efficient, and way easy to roll out with the way that we've done things, and being able to spin things up and swap them out seamlessly. No end users know the difference. You'll also see a couple of load balancers sitting at the top of the stack on this diagram. kind of interesting, I think at least. We have customers that like to white label what we do and use their own domain, use their own SSL cert. So we just terminate those certs at the load balancer. And now instead of services.machineshop.io, blah, 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 they have, their domain.com, blah, 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 that goes with that. And it's exactly the same infrastructure under the hood that's doing that, and nobody's the wiser. So looking at, MVP until now, this was the breadth of the technologies that we used when we first rolled out. The number of requests that we were handling on our inbound side in real time was not terribly high, and it worked really well. As things ramped up, and as we found new and better technologies and brought people on board that had interesting ideas, this is kind of what technologies have been added into the mix since then, and the ramp up in the number of real-time messages that we can ingest over very small time periods. So, and I would say I would credit a lot of that to the ability for us to not pay attention to how much things are costing us and having to plan for 5 years into the future on our hardware and all of that kind of good stuff. Just that flexibility as a developer to be able to concentrate on development rather than having to concentrate so much on infrastructure makes life a whole lot easier. One of the other things that we get to do because of this is we get to do flexible deployment. So we develop everything out in a very modular style. It's very easy for us to take things if at the translation layer of things, which is sort of the outermost part of our stack, listening to messages from the things. If you want to host that yourself and you feel comfortable doing that, awesome, host it yourself. You can still use the rest of our core. There are various bits and pieces of like, if you want to host your own database, great, you can do that. Here's what you need. Make sure we can hook up to it. That's great. So flexible deployments is a huge part of what we're a big fan of here. Just kind of pointing out some of the services that we tie into for AWS. You'll see Kinesis is one of the things that we can integrate with. On the front end of things, moving in, EC2 is a big part of what we do, S3 to some degree, and then notifications and emails are a part of those services that we'll integrate with as well. So, just from a big picture standpoint, a lot of the things that we've learned along the way from an IoT standpoint, you have to be flexible in order to cope with the volume of data that you'll see and the types of data that you'll see and how to process all that data. So lots and lots and lots of horizontal scalability, lots of parallelization to the degree that you can achieve it, and then automating everything. Make your life easy, reduce mistakes, auto scale, all of the goodness and tools that are available to us, lean on them. That's why they're there. People created them for a reason, so let's use them. And I think that's it. Now it's Janesh. So thank you, everybody.
Thank you. Awesome.
Yep.
Thanks a lot.
Janesh, yeah.
Thank you. So just to kind of close on this, I feel every electrically connected device or appliance is going to be internet connected in the next few years. So how we can build a better, great architecture that can not only scale, but also really build out some of the basic ways of scaling and user experience and the best practices that come along with it. So I would like to thank all our customers, Zach, Kyle, and John, and please give a round of applause for them for coming all the way here and presenting the best practices. Thank you. Thank you very much.